Yes, perdón. Voy a tomarme unos minutos para presentarlo y entonces voy a cambiar a inglés para presentar al Dr. Qin Lin. So, Dr. Qin Lin, he's director of Azure and Intelligent Robotics Lab at the University of Houston. So we're really happy to have you here. He's going to present the topic from fiction to function, safe and reliable robotic control under the three laws. So that's a really interesting topic, and I'm sure it's really relevant for the mechatronics students here at the university. So we're really happy to have you here. Now, Dr. Qin Lin has been a tenure-track assistant professor in the technology division of the Cullen College of Engineering at the University of Houston since 2024. He completed his postdoctoral training at the Robotics Institute of Carnegie Mellon University in the United States in 2021 and earned his PhD in computer science from Delft University of Technology in the Netherlands in 2019. Dr. Lin actively publishes in prestigious conferences and journals in robotics, control, and vehicle technology, including ACC, CDC, IFAC, IROS, ICRA, and various IEEE transactions. He serves as an associate editor for respected journals, such as IEEE Robotics and Automation Letters and IEEE Transactions on Vehicular Technology. His research is currently supported by grants from the National Science Foundation, NSF, and the US Department of Education. So please, let's give a warm welcome to Dr. Qin Lin. And
thank you very much. Thank you. Thank you.
And I cannot think of someone better to present this topic. So please go ahead. Okay. The floor is yours.
Thank you. Thank you so much for the introduction, Professor Gonzalez, right? It's my really pleasure to be here. It's my first time to be in this country, and I can tell that I enjoy every single moment in this great city, and I really love the community, right? It's a very dynamic and fast-moving community. I'm glad to see a lot of young people here today, and I just the first observation I can share with you is that the University of Houston and Ibero we share the same theme color, right? Red and white. So yeah, small world, right? So yeah, today I'm going to share my research topics in robotics and automatic control with Ibero. Actually, starts 2 years ago. Yeah. Summer of 2023, and I invited together. So yeah, I'm very grateful that Professor Ramirez and Professor Gonzalez, you actually return a goodwill, right, to have me today, and I have the gratitude from the bottom of my heart. Okay, and just a little bit about myself. I think we already have an introduction. So I moved continent to continent, right? Of course, my wife complained a lot of that. So my last station was in Shanghai city in China. Then I moved to Netherlands, and I start my adventure in United States. And now I'm an assistant professor in University of Houston. And just a little bit about the University of Houston. I'm not sure if it's kind of familiar with you. And University of Houston is the largest public university, research university in Houston, and one of the largest in Texas. Yeah, because we have UT Austin and we have TAMU, they're also big. So we just one of the largest. And we are very proud to be our university. If you are familiar with the education system in the United States, the category of R1 and R2 are very important. So R1 means that we have the highest level of research activities. And so we are approaching to the milestone of 50,000 students, okay? And we have more than 200 million investments in research. And our campus is very large. I'm not sure if you use acre in your unit system, but we have 900 acres for our campus. And a little bit about our Cullen Engineering School. So we have around 2,000 graduate students, including master and PhD students, and we have more or less 8,000 undergrad students, and we have more than 200 faculty members. So we have 10 engineering majors, 10 engineering majors. So all of them are in top 100, and some of them are even in top 10. And our overall engineering ranking is about 17. I think it's this year's US News ranking. And we have 10 departments. engineering technology, information science technology, they form the technology division. So, and we have other engineering departments, but I think 2 years ago, the technology division and engineering school, they are in 2 units, but now we have been merged. So we are in a single unit. And for myself, I'm jointly appointed by engineering technology and electrical and computer engineering. Okay. So let's start our research content today. And I'm not sure if you have read this fiction, but probably it's older than anyone else in this room. So the fiction is I think the fiction was published in 1950 or 60, I cannot remember. But that was the first time the 3 laws of robotics has been introduced in a field. I'm not sure if you agree with the 3 laws, but let me just list all of them to see if you agree with that. First of all, the robot must not injure human beings, of course, right? And the second one, the robot must obey the orders given by the human beings, right? Because we create the robot must follow our orders, right? And the third one, the robot must protect its own existence. Okay, so if you try to summarize a little bit about these 3 laws, so we can say the robot must complete missions and stay safe, right? The first law and the third law are both about safety, right? One is about the safety when the robot interact with human beings. The other one is the robot must be safe, yeah, for itself, right? Okay. Let's look at some counter example, right? The robot not adhering these 3 laws. The first one I think is happening in a warehouse, right? The robot it just went crazy and tried to attack people around, and it's very unfortunate that the stop button is far away from these 2 workers. And the second one was from a Tesla. Yeah, I can see a lot of Tesla cars running in Mexico City, but sometimes, right, it's not very often, but we have also seen some unfortunate accidents from the Tesla. And in this, I think in this case, the Tesla autopilot was on, and there was no any disruptions to the car, but the car just suddenly turned to left and experienced a crash. Okay, that's two counter examples. Let's see. Sorry. There's a little bit delay and okay, so what we do in our research lab, so just in one sentence, we build safe and reliable autonomy, especially for robotic system. So we have some theoretical foundations, right? The first one is optimization. We do robust optimization, trajectory optimization, and we also do machine learning, safe reinforcement learning, and uncertainty quantification using deep neural network. And of course, I'm also a control guy. I'm proud to be control guy. And we do disturbance observer and rejection control. I think a lot of our colleagues on IBRA are working on that. And I also work on control barrier function. That's a very new popular tool to guarantee the safety of robot. And all of our applications are in robotics. So we have the first category is extreme agile robot. So we do drone operating in extreme case, so like high speed and some of the propellers are gone, so how to safely control the drones. And the second one is autonomous racing car. It's not like the normal car, right? The normal car, the velocity probably is not high, but if you have autonomous racing car, the velocity is high and you will experience very large nonlinear dynamics. And we also work on safe motion control under uncertainty, so like manipulations and lag locomotions. I just showed some cool videos happening in our lab, and the first one is the drone control subject to disturbance from a sloshing payload. So like if the payload is like a full bottle of water, right? So this is like almost rigid body, so it's not difficult. But if you only have the half bottle of the water, so you can see that this is really sloshing. And the center of the moment and the center of the gratitude will change over time. So that's the first one. And we also do racing car control at high speed. So yeah, so for high speed, your control objective will really need to be minimizing the lap time, right? And we also test some, for example, how you adapt to the new service, right? You have some friction change from the normal service to another service, which is unknown in advance. And we also do some safe manipulations. So the manipulation needs to be adapted to varied payload. and the manipulations also must be guaranteed to be safe, right, when interacting with people. And we also do some new stuff like AI-based manipulation. So I can see some colleagues here. You also have these leader and follower manipulators. So what we do here is that we use one as the human for human demonstration, and we collect some data and use deep learning. And after you train the neural network, you can deploy it to the follower manipulator. So you just need the camera as input, and the manipulators can autonomously pick and place. Okay. So I cannot show all of them, but I just want to show some selected demos. So like we also do lag locomotion, like wheeled bipedal robots. So it can, for example, this one, it's not a balancing car. It can change the height and it can auto rotate. And there is another wheel bipedal, so it can climb the stairs. And the last one is about you can change the wheeled. You can change the model. Now it's in wheeled, right? You can change to the point foot, and both of them are based on reinforcement learning. Yeah. Okay, so let's look at why it's difficult to follow the three laws in robotics. First of all, we look at the autonomous system, right? It's a very common architecture for autonomous system. We have the cyber component, right? We have the controller, we have all the computer and all the computer networks in this cyber component. And we also have the physical component. We have sensors, actuators, as well as the physical plant. Okay, let's look at the first one. In the cyber component, right now we are introducing a lot of AI algorithms. AI is good without any problem, right? But sometimes if you have safety critical system like autonomous driving cars and so like Tesla, so you cannot completely rely on AI, right? AI makes mistakes, but if your system is safety critical, you don't allow any mistakes caused by AI, right? And that's why AI sometimes made the thing more complicated in the cyber component. And in the physical components, so we have sensor, physical plant, and actuators. But we also have some unexpected attacks, failures, and disturbance. Let's look at the first one. So if you play with the drones, right, the first very important lesson you need to know is that you need to make sure all the screws is not loose. If you lose any of the screws, the propeller will be gone and the drone cannot be stabilized, right? And the first one is very interesting. There is I'm not sure if it's a little bit small, but there was a drone in Canada. It delivers coffee to a customers, but it was under attack by a raven, right? So that's something we don't expect it in advance. And we also have some unexpected disturbance like in the wind. Of course, this is in lab environment to simulate the real world. But of course, we have a strong wind, right, as disturbance. So all of this making the problem very challenging to guarantee the reliable and safe operation of robots. So today's talk will be divided into three parts. The first one is how to measure the disturbance and how to reject the disturbance. And the second one is that if you have disturbance, how to guarantee the safety. And the last one is that how we can combine some advanced algorithms like AI, machine learning, reinforcement learning with the disturbance rejection to improve the performance. So like today, I will talk about disturbance as a term for more than 100 times. But that's just my story, right? Disturbance is like the very, very strong line to connecting everything together. Okay, let's start with the first one, disturbance, quantification, and rejection. Okay, let's look at a closed loop control system, right? This is, I believe, some students are from mechatronics and you study the control course, you are familiar with that. So we have in a closed loop system, we have reference. Suppose that you have a drone and the reference is like the desired position or desired attitude, right? And you design your controller, right? The controller outputs the control action executed to your plant, and you also have some auto measurement using your sensors, right? This is also a very typical control system. And if you know the precise dynamics of your system, control is very easy because you more or less can predict everything will be happening in the future, right? You all know everything about the reachability of your system. So you can, of course, the control action, you can make sure the output measurements precisely track your reference, okay? But the real world is nasty, right? We have a lot of disturbance from the environment. So like for drone, we have a lot of wind around us, right? For the car, it's running on a bumping road. This type of disturbance is from the external side. But we also have the internal dynamics, because it's impossible to precisely model a dynamic system. You always make mistakes, right? Even though you spend a lot of efforts, you still have a lot of things you cannot model, right? So you have internal disturbance and you have external disturbance. That make your system, you always have some offset from your trajectory to your reference, which is your goal, right? So how to manage this problem? And yeah, the key problem is about how we can measure the disturbance, right? In most of the cases, you cannot use some physical sensors to measure disturbance, because you don't know what's the disturbance, right? For wind, probably you can use some sensor to measure the wind, but some disturbance from the internal dynamics, you have no clue to install any type of the sensors. But instead, what we can do is that we can design some sort of observer. The observer is just from the, you can say it's just an algorithm, right? It's not a hardware stuff. It's just like algorithm. So if this type of algorithm can estimate the disturbance, right? And we try to compensate the influence of the disturbance, that'd be good. Okay. So that's everything about the disturbance estimation. I can give you one simple example about the drone attitude control, right? For drone attitude control, we have 3 dimensions. One is pitch dynamics. The other one is roll, and we also have the yaw. So both of them are just one order dynamics, right? Very simple. But I just use this as a running example. What is disturbance reduction? Disturbance reduction is just you try to minimize the influence of your disturbance, right? And you just need to follow 3 simple steps. The first one, you estimate your disturbance, right? Now in each channel of these 3-dimensional dynamics, I have F1 as a disturbance in the pitch, I have F2 disturbance in the roll, I have F3 disturbance in the yaw motion. And I just need to estimate F1, F2, F3, right? And the second step, right? If your control action and the disturbance, we call it match in control theory, but it's just like your control action, like this one, you have a control action here and a disturbance, you are in the same channel, right? What you need to do is very simple, right? This is your disturbance, right? This is your control action. You just need to have the control action in the opposite direction of your disturbance, right? And then you can cancel them out, right? If you cancel the disturbance out, so what we are going to have is a clean model, right? For clean model, it's nice. It's just like what we want, right? For clean model, you can easily design any short of controller, right? So like even for linear controller, you can handle this attitude control. Yeah. Okay, that's the basic idea of disturbance reduction. And let's have an in-depth look at this demo I just showed to you. And we have the disturbance, which is from the slowing payload, right? When our disturbance reduction algorithm is on, you can see the attitude is stabilized, right? You have no problem with the roll, pitch, and yaw. But if you turn off the disturbance reduction, just use some simple baseline, the PID control. PID has some sort of disturbance reduction, but not in an explicit way, right? If you turn off the disturbance reduction, you just use PID, you can see the drone almost crashed. Okay, and the first fundamental question we need to ask to ourselves is that what kind of disturbance can we estimate, right? Can we estimate all disturbance, or we have some requirement for our dynamic system? That is the very fundamental, I think, component in ADRC theory. I'm not sure all of you have heard about that, but we call it extended state observer. So the extended state observer requires the dynamic system to have a form we call it chain of integrators. So the chain of integrators looks like this. X1 is your first state. The first state derivative is the second state. The second state derivative in the third state, so on and so forth. So if you don't understand this one, just think about some translational dynamics, like the position derivative is velocity, right? The velocity derivative is acceleration, and the acceleration derivative is the jerk, and you can control the jerk. So you can just imagine that. And so if your dynamic system looks like this, you can always design a extended state observer. So extended state observer is just a bunch of differential equations. So this is a differential equation, right? This is another differential equation. And so the difference is that in our new differential equation in our observer, we will have extended state, which is our disturbance. So we have our original state and we extend the dimension to include our disturbance. And what you need to do is, because this is a differential equation, right? You just need to integrate. To integrate, if you integrate, you will always estimate the state and your disturbance, right? So if you think the extended state observer is like a black box, the input is just your control action and your measurement. The output is just the estimation of your state and your disturbance, right? Very simple. The first very important progress in our recent years in our lab is that we really expand the application of ADRC theory. Actually, we don't need this requirement anymore. You don't need to be trained on integrators. Actually, you can deal with a more general system, like we have a nominal linear system, right? A matrix, B matrix, and your disturbance is like nonlinear and can be time invariant. It's very general. And our requirement is that you need to satisfy this bunch of equations. Don't worry about that. I will explain to you what's the meaning of these conditions. But what you need to do is that you give me one dynamic system, right? I will just use this as a certificate. I just check, okay, if you satisfy all of that. If you satisfy all of that, okay, I can design an observer. That's just that simple. Okay, and if you satisfy these conditions, all of your disturbance can be estimated without any bias. You can have unbiased estimation and with explanation convergence guarantee. Okay, let's look at what's the meaning of these conditions. Right? It looks very weird. And this condition, if you try to describe in another way from the classical control system theory, is that there is no zero between your disturbance and output. Okay, let's present what's the meaning of that. Let's look at a two-mass system. Two-mass system, so just like this one. Okay, I have one mass, a second mass, and they're connected with a spring. This is a very fundamental block in mechanical system, right? Just use this as a running example. So if you look at this system, this is not chain of integrators. This is a very general linear system, right? Plus some disturbance like W1 and W2. W1 is from the first mass and W2 is from the second mass. And if you look at the first case, if we have some output measurement, position measurement from the first mass, right, X1, and we have the disturbance, which is W1, from the same side, both of them are from the first mass, right? And you can compute the transfer function. Transfer function is just the description of your input and output, right, relationship. So you can see that if you look at the numerator, we actually have two zeros, right? So in this case, there are two zeros between your disturbance and output measurement. So it doesn't satisfy this condition. If it doesn't satisfy this condition, what's the meaning of that? You cannot estimate this disturbance without bias. So this is a bad example. Okay, and what is the good example? If I have the measurement for the first mass and my disturbance is in the second mass, now you compute the transfer function. If you look at the numerator, there is no root. This is a polynomial, right? You will find two roots, but that one is just a constant. There's no zero between your disturbance and output measurement. So for this case, you can estimate the disturbance, W2, using your output measurement, X1. And does that mean you cannot do anything with the first case? We need to change anything. Well, you need to change something, right? For the first case, what you can do, first solution is that you can place your sensor to the second mass. Then you can estimate W1. The other solution is that it's a very important concept in ADRC. We call it equivalent disturbance. So if you have the disturbance here, right, you can do some transfer to transfer this disturbance to the second mass. Then in that case, the disturbance and your output, they are in different positions. In that case, you can estimate your disturbance, right? So the theory, our contribution of theory is that, okay, the original ADRC theory is only restricted to some specific system. Now we really extend to more broad dynamic system. You just need to satisfy this condition. And it will tell you how you design your observer, right? Because for your observer, you need to know where to place my sensors, right? So if you follow this condition, it can give you a guidance how to place your sensor. That's very important. I think I'm very proud of that. And the second contribution is that because you have estimation, right? Your estimation, you always have error. So what's the bound for this error? So we not only look at the final static state, right? Because we say that we always converge to the true disturbance, but it might take time. So we call it transient phase, right? In the transient phase, what's the error bound for that? That's very important for example, like optimal control, robust control. You really need this gap. So that's the first time we get a very tight error bound for, we call it model based, because in the original ADRC we call it extended state observer, but our new theory we call it model based extended state observer. So for model based extended state observer, we can have very tight error bound, and this error bound is directly from the solution of your differential equation. So it's guaranteed to be the most tight. Okay, so I'm very proud of my students' progress in the theory. I think it's a very big leap in the ADRC theory. So we can apply to more general system, and we have better estimation error bound. And of course, we just have a preprint, I think 2 years ago. Now we have extended to, because what I talk about is single input and single output system, right? We also extended to multi-input and multi-output. So we are preparing for this paper to include all of our amazing progress in the theory part. So if you have this theory, you can do a lot of things. The first application I want to show you is about fault tolerance control of drone. For drone, right? So most often the drone you see is quadcopter, right? So you have 4 rotors. You have 4 rotors, and you can keep balance. So what if 1, 2, 3 rotors? Of course, you cannot lose 4, right? 4 will be, you always have a crash. But what if we lose 1, 2, 3? Can we still control the drone? Have you think about that? The simple answer is that it's still possible. And the first interesting fact of physics I want to share with you is we call it reduced attitude. For example, in this video, 2 rotors are gone, right? You only have 2 opposite rotors, right? You can still control, right? But what you compromise is what? If you want to control the drone from position A to position B, you need to compromise your yaw motion. You can see the drone is rotating around the axis, right? Because because you have less motor, you cannot control everything, and you need to sacrifice the yaw. So from position A to position B, now the trajectory will be what? The drone will be like this, right? Right? You need to compromise one thing. And how we control that? So imagine that the ideal case is drawn like, this is my drone. I'm sorry, I don't have a real drone. So this is my drone, and I have a rotation axis. The ideal case is like my drone is rotating like this, right? But probably I have some case when the control is not good, my drone is like this, right? So what you need to do is that you have this your current rotation axis, right? But you also have your ideal rotation axis. If you align these 2 rotation axes, that's good. Yeah, you can still stabilize the pitch angle and the roll angle. Yeah, you need to sacrifice your angle. Okay, so the drone application is highly nonlinear, multi-input and multi-output. And using our model-based extended state observer theory, you can easily design a couple of observers. You split into some subsystems, and each subsystems, you make sure you satisfy the condition, the ugly mathematical equations I show you. You make sure that all the disturbance can be estimated without bias. Okay, and then you can try to reject the disturbance. And so far, we published a paper in control system letters, but the result is still in simulation. That's one possible project I'm going to work with Professor Ramirez, that probably we can do some more interesting hardware experiment. But in our paper, in this paper, we compare with state-of-the-art work in 2 years, I think 4 years already, 4 or 5 years ago, published in IEEE TIO, and we show that our experience, our performance is even better. And if you look at the experiment, we only have 2 rotors, and what else? we also have a very strong wind, 15 meters per second from left to right. So we have the combination of two very challenging conditions, right? One is you lose two rotors, and the other you have very strong wind from the external world. And the TRO work, they cannot keep the position of the drone, but our drone still survive in this condition. Okay, and I think that's let's look at the key takeaways for the first part. Our labs, we work on disturbance quantification and reduction, and that's the key and fundamental problem for reliable robotics control. Okay, and we developed some fundamental tools for disturbance estimation and with convergence guarantee and tight error bound. That's the first part. And let's move to the second part. In the second part, what's the difference between the first part and the second part? In the first part, we only care about the tracking problem, right? From position A to position B. But in robotics application, sometimes you also have extra requirements. So like you have some unsafe zone, right? For the drone, you don't want to have any collision, right? You have some unsafe zone. And how can you make sure that you can move from position A to position B and you don't have any collision with the obstacle? And the guarantee must be 100%. Okay, we don't allow any possible mistakes. Okay, that's the second part. We call it robust safe control. Now let's look at the control barrier function, how we can use control barrier function to guarantee the safety. Now let's look at another closed loop system, but now it's more advanced. You have a controller which is AI based. It can be deep learning, it can be reinforcement learning, it can be any fancy algorithm, or it can be any legacy controller. You already control something, you already design something, right? It's AI or non-AI, it doesn't matter. But you already have something. The question is that the existing controller, you don't trust it. It might make mistakes. So how can we monitor this existing controller and modify if necessary, right? So the nominal controller, you will output a nominal control action, which is U bar. Okay, and U bar will go through a block, we call it safety filter. The idea is very simple. If U bar is safe, okay, it's ready to go. Okay, no problem. You can execute this control action to your plan. But if it's not safe, we need to compute something safe to override your U bar. Right? Does that make sense? It's like a failsafe, right? It's more, the idea is a little bit about the switching, but it's not really switching because we just need one single optimization to achieve that. Okay, so how to do this? First of all, you need to define your safety problem, right? You need to define a safety set. What's the meaning of a safety set? So for example, hx is greater or equal than 0. For example, the relative distance between your robot and your obstacle, the distance must be greater than or equal than 0, right? That's your safety, we call it safety specification. As long as you have this safety set, and if you have a control barrier function, the control barrier function will generate some field along the boundary of your safety set. If your trajectory is about to leave this safety set, this is not what we want, right? Because we have this, you can look at these red arrows. If you're about to leave this safety set, it will be pushed back to the interior of your safety set. So you always guarantee that the trajectory of your system stay in this safety set. That's the basic idea. Okay, so how to achieve that? We just need a mathematical optimization. We call it quadratic optimization because if you look at the objective function, it's quadratic, right? The quadratic is based on the distance. U is your final control action to your nominal control. Nominal control is something proposed by your AI or whatever, right? So you just want to minimize the distance. And the idea is very simple. If your U bar, okay, if your U bar is safe, so it means that U bar satisfies these safety constraints. If it is safe, what's the final control action? It will be identical to U bar, right? Because the objective function is quadratic. The minimum value you can achieve is just 0, right? Quadratic, right? Quadratic. So that's why if U bar is safe, you always have the final control action which is identical to U bar. But if it's not safe, if the AI control action is not safe, I will compute something safe, but stay as close as possible to my proposed control action, right? Just like you have a very fancy algorithm, I don't want to intervene very often. If you are good, I can let you go. But if you are not good enough, I will try to stay close to you, but I make sure that the final control action is safe. Okay, that makes sense? That's the basic theory of control barrier function. But the problem of control barrier function, like a lot of optimal control, is that you need precise model. You need your precise nonlinear dynamic model, and you also need precise state, right? Then you can guarantee the safety. But if we apply our robust control barrier function, integrating our model-based extended state observer, what we can achieve is a robust optimization. So like you have your original optimization, right? Now you just need to add the disturbance, right? The disturbance can be caused by model error, can be caused by external disturbance. And you also account for the estimation error bound. We derive a very tight estimation error bound. And we also consider the state estimation error. So what's the meaning of that? Even though you have unprecise nonlinear dynamic model and you have uncertainty in your state, we can still guarantee the safety. Okay. Let's look at the first application. We have a manipulator, and the manipulator, you need to control the trajectory of your end effect. It's like this fist, right? Or we call it end effector. You need to control the trajectory. And our control problem is that I have a boundary here, right? Just like a human being or standing like this. And you cannot touch me because that will be a safety issue, right? And the robot is not allowed to cross the boundary of your safety set, okay? And what's the uncertainty in this case? We only have the out loop control axis. We can only control the kinematic commands, so like position and velocity. You have no idea about your interloop controller. So this is one source of disturbance, right? The other one is that you have uncertain dynamics because you don't have very precise modeling for your robotic manipulator, right? And the other one, we also add up some external torque disturbance. Well, a lot of disturbance. But if you look at the final result, I'm sorry, this is, I think the safety boundary is here, right? And the blue one is our final trajectory. There is no any collision or cross the boundary behavior for the safety set. And the red one is our reference. Okay, the reference says that you need to follow this A shape, the infinity shape trajectory. But when the robot approach to this area, right, it's at a safety boundary. If you require me to cross the boundary, our safety controller will kick in. No, don't do that. Yeah, you need to keep safe. So that's why our final trajectory will not exactly follow the reference, because the reference is wrong, right? Even though you require me to do that, but I know my safety problem, I can always guarantee the trajectory is in front of the whiteboard, okay? But if you applied traditional control barrier function, there's no guarantee. The end effector will push the boundary, and imagine that this is a human worker, right? It will hurt the human worker. Okay, that's a very simple demo. I show you the power of our safe control. And I think let me summarize the key takeaways here. And the first one is very important, even though you forget about everything of my mathematical equation or whatever observer design today. You need to keep in mind one important concept is that AI is good, but if you apply AI to safety critical system, you cannot always trust AI. The AI-based controller or any legacy controller, it must be always monitored and intervened if necessary, right? I think in this area is also becoming a very popular. We call it AI safety, right? And the second one is that our fundamental tool, we call it robust control barrier function. It can overcome the traditional control barrier function fundamental limitations. We don't need precise model. We don't need precise state. We can still guarantee the safety. Okay. Now let's move to the third part. I believe the third part will be a little bit brief because that's all the theories in the first one and the second one. The third one is that how we can combine machine learning, supervised machine learning, and reinforcement learning with our disturbance estimation to improve the performance for disturbance reduction control. Okay, let's look at how machine learning is used in control problem, right? So imagine that you have a not precise model, we call it nominal model, and you have a true model, right? You cannot even, it's not possible to get the true model. You always have a nominal model. But every time you can estimate the difference between your predicted state and the true state, right? If you look at this I think it's the dynamic system in discrete time, right? In discrete time, your next state is equal to your dynamic model times your time and plus your previous state, right? If you can estimate the difference of the two states, you can estimate the difference of the two models, okay? And the difference of the two models, we call it discrepancy, or people also call it residual learning in machine learning domain. And you can use a deep neural network to capture the difference between these two models using supervised learning, okay? And if you have this residual error from the neural network, what you can do is that you have your original model and you add up the residual error. And you hope that this final model will stay as close as possible to your true model. That's the basic idea of machine learning in control theory. Okay. And as long as you have this adaptive model, right? You have nominal model, always add a neural network. You can design the controller based on this adaptive model, right? If you look at this demo in our E-class work, I think last year. So we work on racing car, and the racing car is a difficult problem because when your speed is high, you will have a lot of friction. You have non-linear tire model, and you also have some aerodynamics, right? That's a very challenging problem. And if you don't have any adaptation, you just use some unprecise model, you can see that after 3 laps, your racing car experience a crash. But if you have some learning for the disturbance or for the uncertainty, you can always achieve minimum lap time, and the car is always safe, staying on the track, okay? But what's the, we also have another demo which my student changed the friction. We just, you have an original friction from your original ground, right? Now you use some cardboard and you change the friction, and you can see the car is still available, is still able to adapt to the sudden friction change, right? You can still, the control is still adaptive and safe. And the limitation for machine learning is you need to collect a lot of data to train the neural network. And during this training, you don't have any guarantee, right? You need to make sure the neural network will converge at some point, right? So that's why one of our motivation is that our observer approach is we have very strong guarantee. And the machine learning, it doesn't have a lot of guarantee. But machine learning is very good to do some linear optimization and learn a lot of prior knowledge about disturbance. Our idea is simple, how to combine them together. Okay, if you look at the dynamic model, we have our nominal model, right? Not precise model. And we have some internal disturbance caused by our model error, right? And we also have some external disturbance from the environment. And our idea is very simple. What if you can learn this part using machine learning, right? Because there is one very important concept in control theory that's called there's no free lunch. You can use your observer to estimate everything, right? Which means that the disturbance is very large. It changes very fast. If you increase your observer gain, you can track, you can still estimate. But if you increase your observer gain, so just like the control gain, the system is very easy to be unstable. It's very easy to be sensitive to your noise. So you cannot always increase the observer gains. But if you have some machine learning, means that some of our disturbance can be known in advance. So like the racing car, right? From the racing car, because every time you run on the same lap, a lot of disturbance is repeated, right? If you can know this type of disturbance in advance, you can reduce your uncertainty. If you reduce your uncertainty, there'll be a less drop left for the observer. Okay, that's the simple idea. And so in our casework, so we propose something we call it disturbance rejection guarded learning. So it means that in our system we have in our closed loop learning system, we have the forward path. The machine learning can provide some prior information, right? We can learn this part. And hopefully, if your learning is good, you reduce the burden of your for your observer, right? And in the feedback part, even though you make some mistakes for your machine learning model, it doesn't converge and it has some error, it can be compensated by your observer. So yeah, you can learn whatever you want, but you always have some guarantee, right? Because my observer will always compensate. So this feed forward and feedback correction loop it's like 2 cycles. It will make sure your learning always has guarantee. Okay, that's our basic idea. And we are working on some experiment for the autonomous landing. So for autonomous landing, it's also a difficult problem. And another fun fact for the autonomous landing is that when your drone approach to your ground, you have some turbulence, right? We have some fluid dynamics students here. So that turbulence is a sort of disturbance. This disturbance will make your drone bouncing back, right? You try to land, but I will not allow you to land. So this is the turbulence. So the disturbance rejection is about how to fight with this disturbance. I want to land, right? And you can see some failure case, right? You have some tipping over if you don't account for the disturbance. And this landing is pretty successful. And let's look at some comparison, right? If you only use deep learning, so how we use deep learning for the landing? You just take off, landing, you collect a lot of data, you learn the disturbance, and you try to design an optimal control based on that. And we just change a little bit. If all the data is from this ground, I think the testing environment is still good. But if you change your ground to a grass ground, your landing will be not successful. Because for different property of your ground, it has different property of your disturbance. And the machine learning doesn't generalize well to different environment, right? You can see you have some collision here. But if you only use model-based ESO, so like our very strong disturbance rejection control, and because we have a lot of this noise, and we use small observer again, it's safe, but the landing is still not successful. You still have very small gap between the ground and your drone. But if you combine them together, right? Machine provides some prior information and observer try to compensate. The landing is successful and smooth. Yeah, the last one I want to share with you, I think very briefly, because we're running out of time, is about how to use this disturbance guarded learning in reinforcement learning. I'm sorry, reinforcement learning is always multi, right? And what we try to do is that for reinforcement learning, we call it IL, right? Let's just call it IL. For IL, you have something we call it replay buffer. You always need to interact with the environment, collect some data, and then you store it in the buffer, and you try and error. Right? In this replay buffer, it's very important to keep all your control actions safe, because you're going to learn some safe policy from the data, right? You need to make sure your control action is safe. But if your model is imprecise, and you want to account some uncertainty and model error, so what we need to do is that you have still remember we have this robust control barrier function, right? For you have some nominal model, and you have some learning, and you have some robust optimization. You combine all of them together and make sure that all the action in the replay buffer is safe. That's the very basic idea, and you can check out our IROS paper this year. And we do some experiment. All the learning is like hardware learning. We don't learn in the simulation, because for simulation you learn and you deploy it to the real world. You always have some gap. But we just do IL in the hardware. So in the hardware, this is our approach, and we compare with some baseline. So for example, this one, you don't have any control barrier function. This one, you have some control barrier function, but the model is imprecise, right? And we can look at the final results. This is our final results. And the control objective is very simple. We just want to learn a navigation policy. I want to navigate the car from position A to position B, right? And I have some unsafe zone, right? I want to make sure I have the minimum commute time. Yeah, moving forward and back, I can achieve the minimum time. And also, I need to avoid any collision with this unsafe zone, right? If you look at the final trajectory, we don't have any intersection from the trajectory and unsafe zone. But this baseline, you always, these two are very terrible, right? You have collision. And this one, you have, probably you don't have any collision, but the time is not optimal. So we achieve safe performance and minimum commute time using RL and using our robust control bias function and disturbance reduction. Yeah, I think that concludes my talk today. And I hope that this trip I come here to make friends, not just with two of you guys, but with everyone. And we look forward to long. 50 minutes, okay. Yeah, don't be shy. Yeah, you're just like my students, right? Okay. Yeah. Question here. Yeah.
Okay.
Okay.
You go first.
Hi.
Yeah. Hi.
You can listen? Yeah. So basically, you're saying that we can complement the AI with a controller to make it better. That's the reason. This,
Yes.
if I understand.
Yes.
Yeah.
So your AI is not necessary to be perfect.
Okay.
We have some. You have AI, right? We have something outside the AI. I can make sure that your imperfect AI is safe enough to be implemented in my robotic system.
Oh yeah, I
Yeah.
understand.
Yeah.
Thanks very much. Yeah.
Because it's not possible to design a perfect AI and safe controller. It's not possible. Yeah.
Yes, I understand that. So that's my question, basically.
Okay, thank you very much.
A very
Yeah.
simple question.
Sure. Yeah, cool.
Thanks.
Yeah.
Thank you so much, Dr. Qin Lin, to come to this conference. My question is for try to encourage to the students to study more about these themes, about this kind of research.
Yeah.
Because some new class that they have is about IA, about self-driving cars.
Yeah.
And I think your presentation is really good for the students.
Yeah.
So I would like to ask about technical things.
Yeah.
For example, what kind of technology did you use for get your results? For example, microcontrollers, program, software.
Yeah.
Yeah. Could you explain a little, please?
Yeah, that's a very good question. I think I always encourage students to study robotics. It's a very tough area because the learning curve is so steep. It's not like you spend 1 week and you can do something. Robotics is like you need to know everything basically. You need to know the mechatronics. You need to design a basic robot, right? You need to know your control algorithms, and you need to know how to implement. So it depends on your project. If you some of the project you don't have very fancy AI, because AI you need some perception from a camera or from a LiDAR. It's just some simple test bed, right? You can just work on microcontrollers, so like Arduino or something, yeah, something simple. It's not a problem, or STM32. And but if you move to something more system level, right? System level, it means that you don't only have control, you only have planning, you also have the perception. So in that case, you really need a system level. For example, you need to know how to use ROS, and ROS is a very important communication to combine all of these components together. You need to know ROS, and to learn ROS, you need to learn Ubuntu, right? System. You need to know how to code up, and that's very challenging. So some students they feel very comfortable with the hardware, but in the software it takes time, right? So, but some students they feel comfortable with the software, but they need to be solid to really hands-on to work on the screws, right? So I would say it takes time, but I always suggest project-based like experience of all of these robotic techniques. You can form up a team. If you cannot do everything, if you cannot work on both hardware and software, you can have 4 or 5 people, right? I always supervise senior design team. So some students, they have computer science background. Some of them have mechatronics background. You work together, right? And stay together for 1 or 2 weeks, 1 or 2 months probably. And yeah, you're working out. Okay,
Thank you so much.
sure.
Another
Yeah,
question?
you have a question here. Yeah.
Thanks. Sorry, I would like to know from your experience,
Yeah.
which kind of projects can we develop
Yeah.
and trying to implement this sort of solutions?
Yeah. So one project, I'm not sure, I shown a video here, and probably yes, I can show something you can experience. For example, this robot, it's a wheel-like robot. Actually, I spent my summer building it by myself. I do it by myself. And you can get some 3D printed components, and you have Arduino. And what we can achieve is that the robot can change the height. And suppose that I have a robot, I want to move from position, this position, that position, but I have a chair, right? I really need to lower my height and go through and go up again. And there's a lot of disturbance rejection, right? My leg is kicking this robot, and it tries to unbalance the robot. But if you have disturbance rejection control, you can always recover, right? For this type of things, it's not difficult. There's no ROS, there's no Ubuntu. It's just simple Arduino. You just know some simple C code, and just know some simple like PID control,
Yes.
right? You can start with the PID, and then you move to our new algorithms, right? Yeah, this is one I can recommend to you. And the other one I'm also trying to collaborate with Mario is that it's a jumping robot. A jumping robot. So the robot can jump. So how can you achieve like I want to jump high, I want to jump further. And there are a lot of disturbance, right? Because when the robot is flying in the air, there's no disturbance. But when you attach in the ground, you have some disturbance, right? So the robots might tip over. And that's also very simple. You have you design some. I think it's just a TI board. I'm not sure if students study in the C2000, and that's just a microcontroller. You just need some C code, and you just need to that one is also very possible for student project. Okay.
Hello, Python is useful for this for get this kind of prototype.
Yeah.
Python is a good way to get this.
Oh, because it depends on platform, right? Because for Arduino, it's like more compatible. It's just C, right? But the C is like simple C. You don't need any fancy C. It's not any fancy algorithm. Because like if you look at the control algorithm, it's just a bunch of equations, right? That's the beauty of control. If you design in a property way, 5 lines of code, 10 lines of code, you solve the problem, right? Okay. Yeah. Okay. We have one question here. Yeah.
Hi.
Hello.
2 questions.
Okay.
How do you integrate AI into control? What kind of data do you get to the AI to learn?
Okay. So if you look at this this one, let me jump to my slide here. Here, this one, yeah. So this is a very typical supervised learning problem. What data you need to collect is that you have your model, right? So the goal is that you want to measure your model and the true model, because we always have a gap. You want to measure this gap. And you have what data? You have your predicted data, because you have a model, right? You have a model, you have a current state, you have a current control action. You can always predict the next state, right? And then when you move to next step, you will have your true state, right? the true state minus your previous predicted state, you will get the state difference. And if you do the difference of these two equations, if you can get the difference of the state, you can get the difference of your model. So like if you do supervised learning, the y we call the label, right? Supervised learning. So the supervised will be the difference of the state, and the input will be your current state and your control action. And but you need to collect a lot of data. So like each step, you have your x, u as input, and the difference as an output as a label. But you need to continuously run your system, right? Collect probably 10,000 data, and then you do supervised learning. You have a neural network. Usually for control problem, if you don't consider any perception from the camera, the neural network is pretty small, 3 layers, fully connected, and control problem doesn't need a very big neural network. And you can get this neural network, and after you get this neural network, you add up to your original model. You can design your controller. Okay, this is one possible. This is a very famous paradigm for learning for control. Yeah. Okay. Okay.
How much precision do you need to have about the nominal model?
Uh-huh.
And in that case,
Okay.
how discrepancy, well, about the AI control agents must, well, be able to solve the problem.
Okay, so what you mean is that what if this model is so bad, right? There's a huge difference with your true model. I mean, control problem. Another thing you need to know is that every control algorithm, you have your limitation. You cannot reject extremely large disturbance. So like if you put your drone into a hurricane, you cannot control because the disturbance is too large, right? But what control theory tell you is that under some sort of conditions, because I have observer gain requirement, I can reject some sort of disturbance. We can tell you, okay, if you want to fly your drone in a hurricane, no problem. You can scale up. You can build a stronger motor, right? And you can do your control algorithms. But that's the limitation of your hardware, right? Okay.
I have a question on the
Yeah.
control action. And as far as I know, the same control action you use for your AI controller, your regular controller, is the same that you use for your disturbance rejection part. So how do I know the same control action is the most optimal for both cases? Well, for your regular controller and for your compensator.
I'm sorry. I want to understand the question a little bit. Can you start?
Yeah.
Yeah.
Let's say you have the velocity of your motors as your control action for your
Yeah.
regular controller,
Okay.
and your compensator for disturbances also uses the velocity as the same control action. But
Yeah.
how can I know the same one is the most optimal for both of them? How can I have a greater compensation using, well, how can I know I'm having the most compensation using the same control action?
How do you know your control is optimal? So it's like this.
No, like the control action for the, well, for the observer,
Yeah.
it's the most optimal.
How do I know that my observation is optimal?
Yeah, that I'm controlling the most optimal thing with it.
I mean, so the observer, what we can guarantee you is a fast convergence. Suppose that this is your true disturbance, right? It will take, for example, a few steps to get for me to get the true value, right? I can only have this guarantee, but yeah, some because for model-based extended observer, you can also try some nonlinear observer, because what I show here is a linear observer. You can use nonlinear observer. So nonlinear observer, you can have faster convergence. Faster convergence. I think for estimation, the really thing is, one is you need to be unbiased, right? You need to be a true value. The other one is how fast. just keep these two key indicators in mind. I can always guarantee you have unbiased estimation. But if you want to have faster estimation, you can think about nonlinear observer. But nonlinear observer, you have more parameters to tune. That's always a trade-off. Okay. Theory is theory. Okay. I can have this guarantee in theory, but in the real life, it's more difficult. So in a lot of cases, we don't really know this estimation is optimal because your estimation also combined with your observer, with your controller, right? You can only look at an overall performance. If your system can recover in presence of the disturbance, you do a lot of experiment. You try different types of disturbance, and if you can still recover, I would say this is a pretty decent observer and controller. Okay, but you can derive a lot of things for this guarantee, right? In your paper. Okay. Okay.
Es que yo también tenía pregunta.
Hi, thank you for the conference. It was pretty interesting. I'm actually a student that is member of president of the Ibero Drone Club over here at the university. And I would like to know, for the examples of the drones you showed, what kind of hardware do you use? Is it like the commercial grade hardware, or is it something more specialized? Do you build it in-house, or is there something special to it?
Yeah, that's a very good question. I think for our drone, there is one nice thing for our drone is like I think we showed it here. That's a very good thing I want to share with you guys. This drone, because most of the drone nowadays they use PX4 or autopilot as their firmware, right? And the challenge for this one is that the code base is very large, millions of code. Student cannot read all of them. And the nice thing of my drone actually is from China. The nice thing is that you just need to focus on the control part. If you're a control guy, you just need to know Simulink. You design your controller algorithm, right? And the Simulink can automatically generate C code for you inside the PX4. That will be easy your task, right? You don't really need to dig into the C++ code. And I can show this drone with our professors here, and if you can see, it's suitable for your problem. Yeah.
Thank you very much.
Sure. Yeah.
I have
Okay. Yeah. Sure.
well, in one of your slides, you mentioned something about control vary function. I don't know if you have heard about the algorithm A star, the one that
A star is like planning algorithm, right? Okay. Yeah. I can talk about that. So for robotic system, you always have control level and the planning level and the perception level. So A star algorithm is typically used for path planning. So you have obstacle is in this room, and I want to navigate from that position to that position, right? You need to first of all plan a path, right? That A star is very popular. But the problem of A star is in the planning level because it doesn't consider the dynamic of your robot. Just like very A to position B, but you don't really consider the low-level dynamics. So what we typically do in robotic systems is that you have your A star, right? You send it to the low level, and the low level will try to track this path. So they're actually in different level. The control barrier function is the same thing, is that both of them are used for collision avoidance, but the control barrier function is in the lowest level, okay? Lowest level, you consider the dynamics of a robot, and you need to make sure your robot track your A star path and also consider the dynamics and also the uncertainty, disturbance, whatever in the lowest level. Okay. Yeah. Do I answer your question? Okay. Cool.
Yeah.
Cool.
Hello.
Hi.
First of all, thank you for your conference.
Thank you.
It really amazed me.
Yeah.
All about modern control observers has always blown my mind. And what really is my question is not, well, it is related to the conference, but what's the next step for you? Like you already mastered how to avoid collisions.
Yeah.
Well, it's mostly avoiding collisions, like either with people or while landing.
Yeah.
So,
yeah.
like through your eyes, what's the next step, or what are you like researching now?
Okay. Yeah, that's why I really like safety problem, right? I think for safety problem, I can work on decades. Why? If we talk about the safety of an airplane, people are still working on the airplane safety, right? Probably every 10 years you can scale you can improve one scale of the safety. So like you know what I mean? For airplane it's already safe, but there's still a lot of room to improve, right? And now if we look at the robotic system, so autonomous driving, right? It's far away to say it's safe. Okay, even though you consider a lot of disturbance and now what most of the disturbance we consider is from the lower level, right? The interaction of the vehicle tire to the ground and some bumping road, for example, and from the drone wind. But you always have other disturbance. For the autonomous driving, a very very challenging disturbance is what? The human beings, right? You always need to interact with human beings. The human being can be reasonable, can be unreasonable, right? So at what kind of assumption and what kind of degree of safety you can guarantee is still not so problem, right? Because you consider some disturbance from the low level, but you don't consider the people's uncertainty, and you don't consider the perceptions uncertainty, right? So like Tesla, they use a lot of camera, but you can see some accidents if you have a lot of refraction in light, so like it can really destroy your perception part, right? That disturbance I don't consider, right? We don't consider in this level. So how can we design a safety guarantee for the whole system, right? How can we have a holistic guarantee? That's our lab is going to do in the next, I mean, probably for decades. Okay. Yeah. Okay.
Is your AI model actively learning from the non-AI disturbance prediction models?
Oh, so the AI can be anything. So AI can be supervised learning AI. It can learn from human demonstration. So you learn how AI can drive from human data, and it can be reinforcement learning. So like try and error. You don't have any supervised data from the human beings. It can be from both sides, but it doesn't matter. We just assume that we have something already existed, right? It can be AI or non-AI. It can be anything, but we just guarantee the safety of this controller. Okay. Okay.
Yeah. First, thank you very much, Qin Lin, for your talk.
Thank you.
Well, before I close, I also have a question. I have two questions.
Okay.
Actually, so you have the model for when you add this. So you add the neural network to try to approximate better the real model, right? Have you considered what happens when the neural network gives you unexpected results? Because that's something can happen, right? And another thing is you have your training data, and your training data, your X's and U's are for a certain regime of values, right? What happens when you extrapolate from those values? Does the neural network gives you something completely unexpected, and then your controller has to compensate for everything, or?
Yeah. So in our framework, it's like your neural network can be I think it's here.
Okay, perfect. So I would just like to give you some certificate for
Oh,
this
wow.
really interesting talk. Thank you
Yeah.
very much, Dr.
Thank you,
Qin Lin,
thank you.
and hope you.
Yeah, I
Yeah?
want to keep a photo for that
Yeah.
in my memory. Okay. Yeah, so okay, thank you,
Ya nos
thank
vamos a
you.
tomar una foto todos. Vénganse, now we can take a picture.
Okay, okay,
Yeah.
sure. Yeah.
Vénganse.
Okay, probably I can switch to the title page, and that'll be nice. I switched to the
Las
title
personas que
page.
nos dieron en
Yeah,
Zoom,
thank you.
muchas gracias y
Yeah.
nos vemos en el siguiente seminario.
I'm sorry.
Hasta
Oh,
luego.
sorry to- Yeah. Do I call something?